Okay, then now I think you guys can hear me. Yeah, please let me know if you guys can hear me. There must be some technical issue. Oh yeah, I just reconnected it to the audio. I'm sorry. Yeah, that was the unit part. I just did one single, very simple example question, for this unit conversion problem. And next, okay, here are more example questions regarding the unit conversion. So now, this time, rather than doing a unit conversion between the same units or the units of the same quantity, such as the mass, now I'm gonna do the multiple different types of the unit conversion. What I mean by that is now I am given kilometers per hour. So kilometer is a unit that's used to measure the length, or the height, and hour is a unit used to measure the time. So these two are two different types of the units. So I will have to do at least two times of the unit conversion. So how I convert between 21 kilometer per hour and meters per second is it's actually the same. Okay, so how do I go from kilometers to the meters? So I know that 1 kilometers is equal to 1,000 meters. So the unit conversion factor between them must be either 1 kilometers over 1,000 meters or 1,000 meters over 1 kilometer. Then what about the hours and seconds? Well, 1 hour, we know that it's equal to 60 minutes. And then I know that 1 minute is equal to 60 seconds. Okay, then 1 hour is equal to 60 times 60, which is 3,600 seconds. So the unit conversion between the hours and seconds must be 1 hour over 3,600 seconds or 3,600 seconds over 1 hour. Okay, now I'm gonna do the unit conversion. So 21 kilometers per hour, and how I'm gonna write it is instead of kilometer slash h, I'm gonna write it as 21 kilometer divided by 1 hour, because that's basically the same. And then now I will have to multiply it by some kind of unit conversion factor to get meters per second as the unit. And meters per second is the preferred unit that I want. Then I know that I want to cancel out kilometers and then have meters instead when it comes to when it comes to length unit. So I know for sure that similarly as what we did in the last example question, I want to cancel out kilometers, so I put kilometer in denominator and meters in numerator. So in between these two, I'm going to pick this one, meters over kilometer. So it must be 1,000 meters over 1 kilometers. Okay, so now I successfully canceled out the unit of the kilometers and then left with the unit of the meters, but I still have the hours. Yeah, I still have the hours. So to cancel out the hours and convert it into the seconds, what I have to do is exactly the same. I want to cancel out hour. The thing is, this time I'm not going to put the hour in denominator because the hour is already in the denominator. If I want to cancel it out, it has to be in numerator this time. So the hour has to be in numerator, and then instead the second has to be in denominator because eventually I want to have per seconds, which means seconds is the denominator. So out of these two, okay, which one fits the unit? Hours per second. That's going to be the first one. So now it becomes 1 hour over 3,600 seconds. And again, this time the hours is canceled out. And as for the numerical value, it just becomes 21 times 1,000 divided by 3,600. And then the unit is meters per second. Again, I'm not going to deal with the arithmetic part because everyone can do it using a calculator. Okay, this time, what about the second one? 56 meters per second, and let's convert it into the unit of kilometers per hour. Okay, so again, I'm going to write it in terms of 56 meters over 1 second. And I want to cancel out the unit of the meters. So I must put meters in denominator and kilometers in numerator. And we know that the conversion between the kilometer and meters is 1 kilometers is equal to 1,000 meters. So it becomes multiplied by 1 kilometers over 1,000 meters. And again, I want to cancel out the time unit seconds and then convert it into hours. So I need to put seconds in numerator and hours in denominator. So this way, meters is canceled out. The seconds is also canceled out. And the conversion between the seconds and hour is 1 hour corresponds to 3,600 seconds. So eventually that's going to be 56 multiplied by 3,600 divided by 1,000. And the unit is kilometers per hour. Okay, so the last one, why don't you guys try it by yourself? So 87 miles per hour, and you need to convert it into meters per second. So this is miles per hour instead of kilometers per hour or meters per hour. So you will have to do one more step of the conversion to convert the miles into the kilometers, and kilometers into the meters. And then you also need to convert the hours into the seconds. Okay, so this is how I do the last one. So 87 miles per hour, 87 miles over 1 hour. And the first step is to convert the miles into the kilometers. Again, I want to cancel out the unit of the miles. So I put the miles in the denominator and the kilometers in numerator. So it becomes 1.6 kilometers over 1 mile. By then, the mile unit is canceled out. And then I want to convert the kilometers into the meters. So I put meters in numerator and kilometers in denominator. So it becomes 1,000 meters over 1 kilometer. By then, kilometers, the unit kilometer is canceled out. And then eventually, the last step is I want to cancel out the unit of the hour. So I'm going to put hour in numerator and in the seconds in denominator. Again, the reason I put the hour in numerator is because in the given physical quantity, 87 miles per hour, the hour is in denominator. To cancel it out, I need to put in numerator. Okay, so hour is canceled out, and then the conversion, the numerical value of the conversion between the hour and second is 1 hour to 3,600 seconds. So eventually, the numerical value should be 87 times 1.6 times 1,000, and then divided by 3,600. And as for the unit, that's meters per second. So if you can do all of these 3 questions, then I think you should have no problem with the unit conversion. Okay, so I'm gonna jump to the next section, which is the prefix. So what we mean by the prefix is the mega, the giga, or the pico, the centi, milli, all of these. This stuff that we put in front of the unit. Okay, so let's say every month I use like 40 gigabytes. So what it actually means by the gigabytes is it means 10 to the power of 9. So 40 gigabyte is the same as 40 times 10 to the power of 9 bytes. So byte is the unit that's used to represent how much of the data you use. So like about 10 or like 15 years ago when the data just came out when I was in like middle school, we didn't use that much of the data. Back then we used the KB, the kilobyte, and then MB, the megabyte, to represent the amount of data. And these days, because the technology has developed so much, so we can use the data on the level of, on the scale of the gigabytes. So the megabytes and gigabytes, they're basically the same. They're basically on the same unit, but just on different scales. And on the right hand side, we have the scientific notation. And what I mean by the scientific notation is it's just a way, it's just a method to write a number in science and in math. So a scientific notation means that you have to multiply a number by 10 to the power of something, 10 to the power of a whole number. Okay, and as for the whole number, it can be 0, 1, 2, 3, 4, 5. It can be -1, -2, -3. My bad. It should be integer rather than a whole number, because whole number is only a non-zero number. My bad. It should be the integer. Okay. And then as for this number, that's multiplied to the exponent of 10, it should be a number that is greater than 1, but that's greater than or equal to 1, but that is less than 10. So you cannot write something as 10 times 10 to the power of 3. Okay, this is not a correct way. That should be written as 1 times 10 to the times of 4. This is the right way to write it in scientific notation. Or 0.3 times 10 to the 5. This is also not correct because 0.3 is less than 1. So we should rewrite it as 3 times 10 to the 4. So you multiply a number that's in between 1 and 10 by 10 to the power of an integer. Why do we use this? Why do we use the scientific notation? It's just a convenient way for us to represent a number, because you don't want to write this many of the zeros when you actually do some kind of calculation. So let's say every month you have like 10 gigabytes or 20 gigabytes. You don't want to get a text message saying that, like, dear customer, this month you have like 20 gigabytes, but rather than GB, it just writes like 9 or like 10 zeros. So like that's not something you want to see. We always look for convenience. And in science, in high school chemistry, in high school physics, actually you only need to be familiar with the giga, the mega, kilo, and then the centi, milli, micro, and nano. The other three, deci, deca, and hecto, are not used that often. Okay, and the next, that's going to be vector versus scalar. So I do consider vector as one of the most important concepts that you need to know before you learn the physics, because all of those physical quantities, they are categorized into either vector or scalar. So it must be one of them. Okay, so the primary difference between the vector and the scalar is that scalar has magnitude only, while the vector has both magnitude and direction. Okay, so what are some examples of the scalar quantity? So a lot of stuff that you use in real world as scalar quantities. Okay, so let's say I'm going to describe how somebody asked me how tall I am, and then I say, oh, I'm 5'4". Okay, so you're not going to describe yourself as 5'4" to the north, 5'4" downward, or 5'4" or to the left. Yeah, it's just 5'4" or 5'6", 5'10". It's just a magnitude itself. So the height or the length or the area, the volume, that's the scalar only. Or let's say like you are looking for a new apartment, and then you're let's say this apartment is 1,000 square feet, 900 square feet. There's no such thing as 900 square feet upward, or like 10 or 1,000 square feet downward. Then the direction is unnecessary when it comes to describing the area of an apartment. So those are the scalar quantities only. And also the same for the density, also the temperature, the pressure, energy, work, and power. So all of these, the energy, work, power, the length, speed, mass, these are the physical quantities that you're going to learn in AP Physics 1. On the other hand, vector means that it has a specific direction and a magnitude. So let's say your mom is asking, okay, Yuhyun, where are you? Are you going out tonight? Like, where are you going? Where are you going with? And how far are you going away from home? So let's say, oh, I'm gonna visit a bar, which is 2 miles away, and it's in, let's say it's in DTLA. It's to the east from where I live. Okay, 2 miles away to the east. Okay, this is a very specific way to describe the displacement. So it has the direction, which is to the east. It also has the magnitude, which is 2 miles. So this is what I mean by the vector. So velocity, that's also similar. So velocity and speed, the major difference between them is speed only describes how fast you're moving. So you can move to the left or to the right or upward, downward, to the north, to the east, southwest, and then you can still have the same speed. But when it comes to velocity, moving to the left by 1 meters per second and moving upward by 1 meters per second are completely different. They are considered two separate or two distinguished velocities. And then the next is acceleration. Again, we derive the definition of acceleration from velocity, so that's also the vector. We're going to talk more about the definition of the displacement, velocity, and acceleration later when it comes to kinematics. And the momentum, because when we calculate momentum, we also use the velocity. Momentum is equal to mass times velocity. Mass is scalar, but the velocity is a vector. So eventually momentum also becomes a vector. And force, that's also a vector. So the very basic definition of a force is, okay, think of when you're hitting someone. So when you're hitting someone, you must be hitting him or her like either, okay, in their face, right, in their, I don't know, like in their tummy or whatever. So there must be a specific direction. Either you're punching them this way or this way or this way. There must be a specific direction that comes with the force. So force is also a vector. And then the electric field, magnetic field, etc., a lot of other physical quantities are the vectors. But again, in AP Physics 1, we only deal with displacement, velocity, acceleration, momentum, and force. Okay, and next, then how do I do the operation on the vectors? When I say operation, I mean addition, subtraction, and multiplication and division. I mean, here we're not going to deal with the division. We're going to only deal with the addition, subtraction, and multiplication. So first off, how do we add the vectors? Well, for now, let's do not consider the physical quantities. Let's only consider vector as the mathematical concepts. So here are two vectors, and let me represent them graphically. Okay, here I have vector 1 and vector 2. So when you add up these two vectors, there are two methods. One is parallelogram method. The second one is tail to tip method. So let's talk about the first one. The first one, the parallelogram method, what you do is you always put their tail together. Okay, so this is what we consider tip. This is what we consider tail. Okay, because it always starts from the tail. It starts from a point and then it points away from this point toward another direction. And then this is a starting point. This is the end point. The end point is what we call by the tip, and this is the tail. So we put the tail of these two vectors together, and then what I'm gonna do is I'm gonna draw the parallel lines of these vector. Okay. So the parallel line for this vector is this way. Again, I'm going to draw a parallel line for this vector, vector 1. And then I'm going to move it to the tip of the vector 2. So now it forms a parallelogram. Okay, here we have a parallelogram. And for this parallelogram, what I do is I always start from one. I always start from the tail that these two vectors share. So I start from this point, and then I just go all the way across this parallelogram along the diagonal. So this diagonal represents the sum of these two vectors, vector 1 and vector 2. vector total is equal to vector 1 plus vector 2. And this is what we call by the parallelogram method. So this is one way to do it. And then the second way is going to be tail to tip method. Okay, so tail to tip method can actually be more, it can be more useful because tail to tip method can apply to more than 2 vectors, while the parallelogram method applies to only 2 vectors. Okay, so let me label this. This is parallelogram method. So only 2 vectors. If you have more than 2 vectors, then you cannot use this parallelogram method. You need to have, if you have more than 2, like 3, 4, 5 vectors, then you have to use the other one, the tail to tip method. Okay, now let's talk about the second one, which is the tail to tip method. Okay, so now let's say I have more than 2 vectors. Let's say 3 different vectors. Okay, so this is vector 1, and let's say this is vector 2, and then this, okay, and then let's say this is vector 3. Then what I do is, instead of putting all of them all together and then on the same tail, what I do is I just connect them one by one. I just connect the tail of the second vector to the tip of the first vector. And then I connect them by putting the tail of the third vector to the tip of the second vector. Okay, so vector 1, vector 2, vector 3. So eventually, what I do is I start from the tail of the first vector. This is vector 1, this is vector 2, this is vector 3. I start from the tail of the first vector and then I end at the tip of the third vector, which is the last vector. And then I connect them with a straight line. Then now this is the sum of these 3 vectors, vector 1 plus vector 2 plus vector 3. So this method is especially useful and powerful because you can handle a lot of different vectors. Again, does the order matter? The order doesn't matter. You can do vector 3 plus vector 2 plus vector 1, and you will still get exactly the same result. Or you can do vector 1 plus vector 3 plus vector 2. Again, you will get exactly the same result. Okay, let me try to represent it. Okay, this is vector 1. And this is vector 3. So let's say I want to start from vector 3 and then add vector 2 on top of it. This is vector 3, and then I added vector 2, and then I added the vector 1. And again, I start from the tail of the vector 3, and then I end at the tip of the vector 1. And let's try to connect it and see what's going to happen. Okay, so this is going to be the resultant of the vector 3 plus vector 2 plus vector 1. And let's see if these 2 vectors are exactly the same. Well, you can tell that these 2 vectors, they overlap perfectly, and then they are exactly the same, which means the order doesn't matter. Okay, so that's how I add up the different vectors graphically. So later we're going to talk about how we do it algebraically, but here you have a basic idea of what it means by addition of the vectors. Okay, then next, how do I multiply a vector with a scalar? So when I say multiply with a scalar, I mean multiply by just a number, like multiply by 3, multiply by 2.5, multiply by -5, multiply by -7, etc. Or multiply by -1/2, or multiply by 0.1. Okay, so this, let's say this is a random vector, vector 1. Let's just call it vector, or vector A. Let's call it vector A. So what happens if I multiply vector A by 2? So 2 times vector A. Okay, 2 times vector A, that's the same as vector A plus vector A. So what happens is I'm just going to add up these two identical vectors. Okay, so again, I start from the tail of the first vector and then I end at the tip of the second vector. So now this becomes then vector 2 times vector A. Okay, so now you observe that vector A and then twice of the vector A, they are pointing in the same direction. They're pointing in the same direction. So they're parallel to each other. And then the only difference between them is vector 2 vector A is twice as long as vector A. So when it comes to magnitude, 2 vector A is twice as big. But when it comes to direction, they're exactly the same. So when you multiply a vector by a scalar, it results as the same direction. But magnitude changes by whatever the factor you multiplied. If you multiply by 2, then it becomes twice as long. If you multiply by 3, it becomes 3 times as long. If you multiply by 1/2, then it becomes only 1/2 as long. Okay, now, what if I multiply vector A by a negative value? What if I multiply by -1? Okay, if I multiply by -1, then it becomes negative vector A. And then negative vector A looks like this. So negative vector A is pointing in the opposite direction of the vector A. So they're still parallel to each other, but one is pointing in the right top corner, the other one is pointing to the left bottom corner. So vector A and vector -A, they have exactly the same magnitude. They have same magnitude, but opposite direction. Okay, once you know how to multiply a vector by a scalar, then you know how to do the subtraction of a vector. So let's say I have two vectors, vector 1 and vector 2, and I want to do a vector subtraction. This is vector 1, this is vector 2. Okay, if I want to do the vector addition of vector 1 plus vector 2, then this is what I do. So I'm just going to use the tilde method to put vector 2 at the tip of the vector 1. Then this is the addition of the vector. What if I want to do vector 1 minus vector 2 instead? Okay, vector 2 minus vector 1 minus vector 2 is the same as vector 1 plus negative of the vector 2. This is basically what you learn in elementary school math. Like 1 plus 3 is the same as 1 minus 3 is the same as 1 plus -3. So instead of doing the subtraction, what I do is I just do an addition of the negative vector 2. Okay, so this is vector 1, and this should be the negative vector 2, pointing in the opposite direction. So now I'm going to start from the tail of the vector 1 and then the tip of the negative vector 2 and connect them with a straight line. And then now it becomes vector 1 minus vector 2. This is vector 1 plus vector 2. This is how we do the subtraction of the two vectors. Okay, next. So I'm going to briefly go over what it means by the dot multiplication and cross multiplication, even though this is not something required for AP Physics 1, but I think it really helps to understand why some of the equation works in a certain way, because I heard complaints from some of the kids saying that, physics should be calculus based, and then people like College Board make it algebra based, which makes it pretty much more complicated or confusing. But actually, it's just that there are certain assumptions, such as some of the physical quantities is constant, or we do not consider the cross multiplication. So that's why it just becomes a little bit confusing. Okay, so let me try to explain the cross multiplication first. So as for the cross multiplication, I bet you have heard of the right hand rule. So let's say there are two vectors, A and B, and this is where A is pointing at, this is where B is pointing at. This is A and this is B. Okay, then a lot of times this is where A cross B vector is pointing at. So using my right hand, so let's say this is the direction of the vector A, and then this is the direction of the vector B. Okay, so this is A, now this is the B. Okay, and then where my thumb is pointing, which is upward, is the direction of the A cross B. We read it as A cross B. So the cross multiplication works only in three-dimensional world, but we all know that in AP Physics 1, we do not deal with something with three-dimensional reference frame. We only deal with the two-dimensional ones. And you wouldn't see any formulas that has cross multiplication involved in AP Physics 1. So you don't have to worry about that. But in AP Physics 1, you will see some formula that is the simplified version of the dot multiplication, such as work is equal to force times d times cosine theta. So dot multiplication, again, there are two vectors, and then let's assume that they're pointing in two separate directions. So this is vector 1, this is vector 2. Vector 1, vector 2. And what it means by the dot multiplication is, okay, so vector 1 dot vector 2, that's going to be the same as the magnitude of vector 1 times the magnitude of vector 2 times cosine theta. And what happens when you multiply a vector by the cosine theta? Okay, so now I'm going to try to make a right triangle by drawing a vertical line to the vector 2. Okay, this is a vertical, this is a right triangle. So vector 1 times cosine theta, okay, this represents the magnitude of vector 1. Think of it as just the magnitude, not considering the direction. Then magnitude of vector 1 times cosine theta, this is theta, it is going to be this part. So this is hypotenuse, this is the angle theta, this is the adjacent. So it becomes the adjacent. So what it means by the dot multiplication between two vectors is there are some kind of interaction between these two vectors or these two physical quantities, but only the parts, only the components that are parallel to each other work. So only when these two vectors are in the same direction, it works. It interact improperly. If they're perpendicular to each other, then for some reason it doesn't work. And I wanna know, like, to what extent these two vectors are involved to each other. So if you're ever trying to calculate the dot product of the two vectors that are perpendicular to each other, you will get 0, which means these two are not involved at all. They do not interact at all because they're perpendicular. They have to have some kind of overlap to interact with each other. And it represents the amount or the extent of the overlap they have. Okay, again, this part is not something you have to know to succeed in AP Physics 1, but it's just going to be better if you have an idea of what it means by dot multiplication. So a lot of things makes more sense. And then next, it's going to be the XY components. And this part is actually extra important. Okay, so XY components. It's really important. And I'm going to talk about it again when I talk about the reference frame later. A lot of times in physics, we use the coordinate plane, XY plane, to represent our system, right? To represent the position, to represent the velocity, to represent in which direction an object is moving. And when it comes to vector, then you need to represent the x component of this vector in the system, or the y component of this vector in the system. Okay, then what do we actually mean by that? Again, this is related to the addition of the vector. So I'm just going to draw a random xy plane. Okay, this is a xy plane we have, and then I'm going to draw a random vector here. And let's just use v to represent this vector. And let's say, okay, then how do I represent this vector? Or how can I go from the origin to this point to eventually get this vector? So what we can do is by using the addition of the vectors. If I combine two vectors and then add them using the tilde method, then eventually I will get this vector that I want. Okay, and how many combinations do we have? We have infinitely many combinations. You can go down and then go up. You can go to the left and then go to the right top corner, or you can go up and then go down. There are infinitely many combinations. But here, we're going to specifically deal with the combinations for which each of these two vectors are they're along the x-axis or along the y-axis. Okay, then there will be only one possible combinations. Okay, along the x-axis. Okay, along the x-axis, it must be this vector. And along the y-axis, okay, along the y-axis, there can be only this vector. Okay, why am I not drawing overlapping with a y-axis? Well, once I just move it to the left, then it overlaps with a y. So this vector and this vector, it's exactly the same. When it comes to vector, its position doesn't matter. When it comes to vector, what really matters is the direction and the magnitude. So this vector and this vector and this vector, they are exactly the same. Okay, so when you use the vector addition, these two vectors add up to this green one. And then we call them the x component and the y component. So we call it Vx and Vy. Which are x components of the vector v and y components of the vector v. Okay, so the thing is, sometimes xy planes are not defined as the regular xy planes that you are familiar with. So what I mean by that is, okay, so let me just use exactly the same method. Okay, it's still the same vector. It's still the same vector v. But now instead of the regular xy plane, which points horizontally and vertically, now I have a slightly different xy plane. So this time, my xy plane points in this direction. Okay, this is x and this is y. Okay, then how do I draw the xy component of the vector v? Okay, again, for the vector, when I draw the xy component, what's really important is represent it in terms of the addition of the two vectors, and one is pointing along the x-axis, the other one is pointing along the y-axis. Okay, and this vector v, it's already pointing along the x-axis by itself, so it does not have the y component, or its y component is equal to 0. So any of the vector can be written as the addition of its x components and y components. The x component of vector v plus y components of vector y. Any of them, any vector in two-dimensional world. Well, if it's three-dimensional world, then it must be vx plus vy plus vz. But again, in AP Physics 1, we only deal with two-dimensional world. Okay, and next, that's reference frame. So reference frame is also really, really important in AP Physics. And if you can properly set the reference frame, then it's going to be much easier for you to solve some of the kinematics problem. Okay, so reference frame is a set of abstract coordinates. So what we mean by abstract is, think of it as imaginary. It's not something that actually exists. So and then you can just arbitrarily define it. It's an abstract coordinate such as xy plane. Again, we only deal with two-dimensional problems in AP Physics 1, so it's not going to be x, y, z. And reference frame is used to specify the position of any object in that frame. So again, what I mean by that is, I want to know the position of this object. Then how do I represent it? Then I need to have a reference frame to represent it. So let's say this is a reference frame I have. Then I can use, let's say 10, 1 to represent the position of this object. Or if I have another reference frame like this, then now this time I can use 1, 9 to represent its position. So that's what we mean by it's an abstract coordinates, and you can arbitrarily set it. It doesn't have to be a fixed reference frame. It doesn't have to be fixed. You can set a reference frame here. You can also set a reference frame here, or you can even set a reference frame like this. And it's used to identify the position of this object. Okay, so there is a big misconception in physics, which is the reference frame is not moving. Okay, so this is completely wrong. Oops. Oh, okay, right here. So that's completely wrong. So, like what is the most common reference frame that we see in real world? That's gonna be the ground or the earth. We compare a lot of stuff to the earth to describe the motion. So let's say I'm walking in the street, or I'm jogging, or let's say I'm doing a morning jog. Then when I claim that I am moving, what I mean is I am moving relative to the ground or relative to the earth. But let's say I am on a car, I'm in a car or in a bus, and the car or the bus is moving by itself, and I'm just sitting there not moving. So I will consider myself not moving if I compare myself to the bus. But if I compare myself to the earth, then I'm actually moving. I have moved from my apartment to, let's say, to the school or to the workplace. So depending on like how you set the reference frame, your position can change, and how you move can also change. So let's say in this example, like the person or the kid in the bus is claiming that he's not moving, he's standing still, but the kid like standing outside a bus is saying that, oh, actually you are moving, and they have this misunderstanding going on, or miscommunication going on, because they're using two different reference frames. So whose reference frame is the correct one? Actually, both of them are correct. Both of them are correct. There's no such thing as the correct reference frame or absolute reference frame. The reference frame is arbitrarily set by yourself. So it's okay to set the ground as the reference frame and then believe that he's moving. Or it's also okay to set the bus as the reference frame and then claim that himself is not moving. Either way, it's correct. Okay, and when you solve the AP Physics 1 question, just remember that once you set a reference frame in a specific question, don't try to change it later. Well, to the next question, you can also change it, but when you're doing one single question, going from A all the way to the F, don't try to change it, because then you're going to get more confused. Okay, then is there any absolute reference frame that is fixed? No, there's no such thing as fixed reference frame. So what about the Earth? Because Earth is not moving. Well, that's also relative. Earth, it seems like it's not moving relative to us because we're so tiny compared to Earth. But compared to the sun, Earth is actually moving really, really fast. Earth is moving at, I think it's at 26 million kilometers per day. Kilometers per day. That's the speed of the Earth. That's the speed of the Earth moving around the sun. So the Earth is actually moving really, really fast. It's just that we don't feel it. So we feel like Earth is stationary and it's fixed. Actually, it's not. So let's say I set the Earth as my reference frame. Then is it fixed? Is it absolute? No, it's not. Okay, then what about the sun? Okay, because sun is not moving, and then all of those, the sun and everything, the Mars, everything is moving around the sun. But again, the whole Milky Way is also moving. The sun is also not stationary. If you try to compare with a lot of other stuff in universe. So in universe, we cannot actually find something that's absolutely fixed. But in classical mechanics, we define Earth as something that's fixed, and we define Earth as the absolute reference. Again, only the classical mechanics. So that's it for the reference frame. And okay, so let's say now I'm gonna drop a baseball, so it's moving down. Okay, because I'm claiming that it's moving down, and then I claim that its displacement. I claim that its displacement is negative because it has dropped from a higher altitude to a lower altitude. So now I'm gonna claim that its displacement is negative. It's a negative value. Well, is it always correct? Not always. This is correct only when I define upward as a positive position, as a positive direction. Only when I define the vertically upward as positive y. What happens if I define the downward as the positive direction? If I ever define the downward as the positive direction, then now this baseball is moving toward a positive direction, so its displacement has actually increased. Its displacement is positive. So depending on how you set the reference frame, the physical quantities can change. Well, again, it doesn't mean that all of the physical quantities change, such as work. Work is magnitude, energy is magnitude. It's not affected by how you set the reference frame. But a lot of the vector quantities, the acceleration, the position, and the displacement, the velocity, or the momentum, the force, these are affected by how you set the reference frame, how you set the positive x-axis or the positive y-axis. Okay, and then now it's going to be the rate of the change and then the area under the curve. So this is going to be the last one on the last two topics for class 0 for introduction to physics. Okay, so again, rate of change, there are two meanings when it comes to rate of change. Either I can mean the average rate of change or I can mean the instantaneous rate of change. An instantaneous rate of change in calculus means the first derivative of y in terms of x. And in physics, especially in AP Physics 1, a lot of times the x-axis represent time. So here I'm just going to use time to explain this concept. So let's say I'm going to use the dot diagram to represent the motion of a person. So this is where this person starts. Okay, then the next second, and every second, I'm going to take a picture of this person. For every second. Okay. So based on this dot diagram, you can tell that this person is moving faster and faster, and then he gradually slows down and then comes to a stop. Why? Because the distance between each of the dot is getting bigger and bigger, and here it's the biggest, and then the distance between the dots are getting smaller and smaller and smaller and smaller and smaller. Eventually, they just overlap, which means this person is going fast at the at the beginning, and then he gradually slows down. Okay, here, what I mean by the average rate of change here is the total distance. It's always going to be the total distance, the total value of y divided by the total value of x. And a lot of times it means the total amount of distance divided by total amount of time. And that's what we mean by the average rate of change. But then what does it mean by the instantaneous rate of change? Based on this dot diagram, it's obvious that at every single moment or at every single point, this person is actually moving at a different speed or different velocity. So if I just use one single average rate of change to represent how fast this person is moving, that's not an accurate representation of his motion. So I would rather use the instantaneous rate of change to represent that he's moving slow at first, and then he's moving faster, and then now he slows down again. That's what I prefer. So what happens here is if I ever use a graph to represent the motion, then on the x-axis, I have time. And on the y-axis, let's say I have the position. Then how this graph looks is at the very beginning, the position changes very little. And then suddenly the position changes a lot. And eventually the position does not change much. So this is the type of graph that you expect to see. Okay, and then when it comes to average rate of change, what we do is I just simply connect the initial point of the graph and then the ending point of the graph, and then connect it using a linear line. Connect it using a linear line, and then just calculate the slope. The slope represents the average rate of change. But again, as I said, this is not an accurate representation of how fast this person is moving or how he's undergoing the motion, because he's going slowly at the very beginning and then faster and then slowly. So at every single point, how we represent the instantaneous rate of change is by the slope. Is by the tangent line, the slope of the tangent line at every single point. So let's say at this point, how I draw a tangent line is by drawing a line that has only that's just touching this curve, not crossing it. And at this point, this is how I draw the tangent line. And at this point, this is how I draw it. At this point, this is how I draw the tangent line. And here, this is how I draw the tangent line. So now let's try to compare the slope of the tangent line. This tangent line is relatively flat, so it has a small magnitude or small value. And then this one is a little bit steeper, and this one is much steeper. So now you can tell that the slope is gradually increasing, which means its instantaneous rate of change is gradually increasing over time. And then starting from here, the tangent line is getting flatter and flatter, which means the rate of change is gradually decreasing. Okay, so that's the difference between the average rate of change and instantaneous rate of change. And here, let's try to do some practice. Okay, so on all of this graph, let's try to identify if the rate of change is positive or if the rate of change is positive or negative, and if it's increasing or decreasing. Okay, for graph 1 at the very beginning, the tangent line must be a horizontal line. Okay, and then gradually the tangent line gets steeper and steeper. So the instantaneous rate of change is getting bigger and bigger, which means it's moving faster and faster because it's positioned on the y-axis. What about graph 4? Okay, so at the very beginning, it has a negative slope. It has a negative tangent line. It has a tangent line with a negative slope, which means its average rate of change is negative value. Okay, and then at this point, it's still negative, but it got much flatter, which means it's a negative value, but it has less magnitude, or it's a less negative. And in between these 2 points, it's a horizontal line. Okay, as for the horizontal line, when you try to connect any 2 points on this horizontal line, you will always get a horizontal line as the tangent line. So for the horizontal line, the average rate of change is always 0. What about for this linear line? Okay, non-horizontal linear line. Again, when you try to connect any 2 random points on this line, it's going to give you the same the same linear line, which has a negative slope. Okay, and next, what about graph number 7? So for graph number 7, at first, it has a positive rate of change, and then next it has a 0 rate of change, and then it has a negative rate of change. Okay, and then the last, that's going to be the area under the curve. So the area under the curve in terms of calculus means the integral of y over x, and then it can be positive or negative, because we're not dealing with just the middle school geometry anymore. We're not calculating just the area of a figure. We're calculating the area under the curve rather than the area of a triangle or area of a trapezoid. Okay, so let's see for this example. So this part, it is a trapezoid. The trapezoid has a positive area while the triangle has a negative area. So this part is positive. And then this part is negative. Okay, so what we mean by the positive and negative, it depends on which physical quantities you're looking at. But if we have a velocity here instead of the position, then the positive area means that the displacement is positive, which means it has moved toward a positive direction. If it's negative, then it means that displacement is negative, which means it has moved toward a negative direction. And then eventually when you add them up, you will get an ultimate displacement, which means from the very beginning to the end, if the object has moved toward the positive direction or the negative direction. Okay. So that's it. That's it for the introduction to the physics. So we went over basically everything that you need to know to properly learn the AP Physics 1. And starting from the next class, I'm going to go over the kinematics part. And this is what I'm going to go over um, next Monday, which is position, velocity, acceleration, and 4 of the kinematics equation, and 1-dimensional kinematics problem horizontally, and then the free fall. Well, this is not everything for the kinematics because we still have, like the projectile motion and then more different types of 2-dimensional kinematics problem. So I don't think I can cover everything in one session. So this is what I'm going to cover in the next session.